Welcome back. In this video, we are going to finish chapter 0 with section 0.4 about normed spaces. Okay, so as you know, a norm on a vector space E is a function that associates with each vector x a non-negative number denoted with this symbol, 2 vertical bars. So it's non-negative and it is 0 if and only if the vector is 0. It's homogeneous, so the norm of a multiple of a vector is the multiple of the norm but an absolute value, because so in particular when lambda equal -1 we get norm of x equal norm of minus x, and it satisfies the important triangle inequality. Okay, a norm space, and sometimes called norm linear space or norm vector space, same thing. For simplicity, we'll just say norm spaces. So is a vector space equal to the norm? And as you know, a norm induces or defines a distance. So if you have a norm, we set d of xy to be the norm of the difference between x and y, and then we can easily check that d satisfies the properties of a distance. It's non-negative, it's 0 if and only if the 2 points coincide, it's symmetric, and it satisfies the triangle inequality. So a norm space is a particular case of a metric space, and therefore it's a topological space. So we can talk about, in a norm space, we can talk about open balls, open sets, closed sets, compact sets, conversions, and so on. And a Banach space is a norm space which is complete. So this means that every Cauchy sequence in the space is convergent. And for notation, the closed unit ball of a norm space E is usually denoted by B sub E. So it's the set of elements in the space whose norm is less or equal than 1, and the unit sphere is precisely the set of vectors whose norm is equal to 1. Okay, so these are very important notations. Now, linear operators. A linear operator, as you know, is a function that transforms linear combination into linear combinations. Or if you want, you can split this condition into two parts. It takes sums into sums and a multiple of a vector into multiple of its image. So, and you probably now, if you have a linear operator between two norm spaces, there are 7 equivalent conditions, or 6 conditions equivalent to the continuity of this operator. Because now, if E and F are norm spaces, we can talk about the continuity of any function from E to F. But if that function is linear, then there is an equivalence between. The first condition states that L is Lipschitz continuous, which precisely means that there is a constant k such that the distance between Lx and Ly is less than k times the distance between x and y. So this means that L distorts distances, but in a ratio not bigger than k. Okay, so this is Lipschitz continuity, and we know that Lipschitz continuity implies uniform continuity. Uniform continuity implies continuity even if L is not linear. And linear and continuity implies continuity at the origin. And the fifth condition states that L is bounded on the unit ball. Okay. And condition 6 states that L maps bounded sets into bounded sets. And last condition, the norm of Lx is less than a constant times the norm of x for every x. So I put them in the order because you can do a circular proof. 1 implies 2, 2 implies 3, 3 implies 4, 4 implies 5, 5 implies 6, 6 implies 7, and 7 implies 1 is very easy. Just replace x by x minus y and use the linearity. So a linear map satisfying one of these equivalent conditions is called continuous, of course, or bounded. It's called bounded because of property 6. It's bounded in the sense that it maps bounded sets into bounded sets. And bounded mean in a metric space means that it's contained in a ball. Okay, and I can choose the ball to have any center. Okay. So the space or the set of continuous or bounded linear operators between two norm spaces is, of course, a vector space, because the sum of two linear bounded operators is bounded as well, as you may check, and a multiple of a linear bounded operator is also a bounded linear operator. So we get a vector space that is denoted by L of E and F, and sometimes by B of E and F, calligraphic B or calligraphic L, L for linear bounded and B for bounded as well. And now on this vector space, we can put a norm. It's called the operator norm. So the norm of a linear bounded operator is by definition the supremum of the norm of Lx when x varies in the unit ball, in the closed unit ball. And of course, this quantity is finite because, as by a previous property, L is bounded on the closed unit ball. But this supremum need not be a maximum. Okay, so it need not be achieved. And then it's easy to show that this is really a norm in the sense according to our definition, and to distinguish between this norm and this norm, because this is the norm in F and this is the norm in the space LEF. So we can put the subscript. Okay, but it should be clear from the context what we are talking about. Okay, so, and you can prove actually that several other characterizations of the norm. So the norm of L we can take the sup of the unit sphere. The definition is the closed unit ball, but it's the same actually. You can take the supremum over the unit sphere, or the supremum on the open ball, or we can take the supremum of the ratio of norm of Lx over norm of x for x different from 0. And it's also the infimum of constants satisfying this inequality. Okay? And here actually, it's easy, we can prove easily that the norm of Lx, if L is linear and bounded, is less than the norm of L times the norm of x. So the norm of L belongs to the set, and therefore the infimum is a minimum. Okay, so here the supremum need not be a maximum, but here the infimum is a minimum. Okay, and in the exercise I prove this. Okay, now one result is that if the target space is a Banach space, so it's complete, then L of E and F is also a Banach space. And actually, it's interesting to see the converse is also true. But to prove, so I think we proved this in second year. It's not difficult at all. You take a Cauchy sequence here, and therefore then you use continuity of F to find the element. So it's pretty straightforward. The converse, however, uses the Hahn-Banach theorem that we shall learn in chapter 2. So not trivial. Now we come to the important notion of isomorphism. Okay, here we must distinguish between topological isomorphisms and algebraic isomorphisms. So in algebraic isomorphisms, as well, we didn't define it in. Yeah, we talked about it very quickly. An algebraic isomorphism is just a linear bijection. Okay, but this is not enough for us in function analysis. We need a stronger notion of isomorphism that we call just isomorphism or norm spaces or topological isomorphism. So in addition to linearity and bijectivity, we need continuity of L and its inverse. So otherwise stated, an isomorphism of norm spaces, and we shall use it in this sense actually. So if we just want an algebraic isomorphism, we just call it algebraic isomorphism. So a topological isomorphism is both an algebraic isomorphism and a homeomorphism. So both. So it is something that conserves both the algebraic structure and the topological structure. Okay, and this idea of isomorphisms is very central in functional analysis. Okay, so in any field of mathematics, there's the notion of isomorphism. In algebra, we have the notion of isomorphisms of groups. Okay, so two isomorphic groups are considered can be identified. It's the same. It's essentially the same object. Okay, so for a topologist, we have the notion of homeomorphism. Okay, so two spaces are homeomorphic if they have the same topological structure. So, for example, for an algebraist, the group of symmetries of an equilateral triangle and the group of permutations of 1, 2, 3 are isomorphic, so they can be identified. Okay, we don't really distinguish. Try to write this actually, it's a very good exercise. Okay, for example, the permutation 1, 3, 2 corresponds to a symmetry with respect to a bisector, right? And 2, 3, 1 is the rotation, and so on. So it's the same object. So, and for a topologist, a circle, an ellipse, a square, a triangle are all the same object. They are all homeomorphic, as we saw in the topology course in second year. So otherwise stated, a topologist doesn't distinguish between all these shapes. And for a functional analyst, all n-dimensional normal spaces are the same object, as you know, because they are isomorphic. And continuity here is straightforward, because when you work in finite dimensional spaces, all linear maps are automatically continuous. But for a function analyst, all separable Hilbert spaces are the same object. In particular, the space of sequences L2, it's the set of sequences whose such that the series of general term xn squared is convergent. And the Lebesgue space L2 of 0, 1, which is the space of square integrable functions, actually are isomorphic. Okay, so for a function analyst, it's the same object. Okay, and one problem. So one problem in group theory is the classification of groups. Of course, this is a hard problem. We cannot classify all groups, but we can classify a smaller subclass of groups, of all groups. Okay, a big problem in topology is the classification of a very important class of topological spaces called manifolds. Okay, and this is a big problem. Now, in functional analysis, one of the problems is the classification of Banach spaces up to isomorphisms. Okay, so we want to know when two Banach spaces or two null spaces are isomorphic. Okay. Now, there is a stronger notion of isomorphism, a more rigid one. It's the notion of isometry. An isometry is, of course, a linear operator conserving the norm. Okay, so you can think of it as a rotation, if you like, an analog of a rotation or a symmetry. So, of course, it's automatically continuous and its norm is 1. Okay, now an isometry need not be surjective. If it's surjective, then automatically its inverse is continuous, because the inverse, when it exists, it satisfies also L-1 of x is a norm. So L-1 also conserves the norm. So an isometric isomorphism is both an isometry and an isomorphism, or if you like, a surjective isometry. Okay. So an isometric isomorphism conserves distances. Okay. So it's something more rigid. We may have isomorphic spaces that are not isometric. Okay, so isometry is more rigid. Okay, and now we come to the important notion as a particular case of the space L of E and F is when the target space is the real line. So the space of all linear bounded maps from E into R has a name. It's called the dual of E. and it's denoted by E star, or sometimes by E prime. Okay? And therefore, according to our previous definition, the norm of an element in the dual is the supremum of, here actually we take the absolute value because the norm on R is just the absolute value. So when I say nothing, R is equipped with the absolute value, which is the standard norm. Okay? And because the unit ball is symmetric with respect to the origin, we can drop the absolute value, as you may check. Not difficult. And also a notation, sometimes instead of f of x, if f is an element of the dual, f of x is actually a real number, right? Because f takes value in R. Now, instead of writing f of x, we write fx between brackets. And this notation is reminiscent of a dot product. And there's a reason why we use this, because this form is linear in f and linear in x as well. So it's bilinear. It's like it's a scalar or inner product. And this is very convenient, actually, this notation. And note also that since R is complete, E star is complete, even if E is not complete. So E star is always a Banach space. Now, let us give some examples of dual spaces. Okay, so this will be a review of the fundamental examples of Banach spaces and their duals. So take the simplest Banach space, which is just the real 9. Okay, what can you say about the dual of R? It's a very simple question. Actually, the dual of R is isometric with R, so it's a copy of R. Okay, so we can identify the dual of R with R itself. How do we know that? Okay, consider this very simple operator from R to its dual. So here I write R star for the dual of R and not for R without 0. Okay. Okay. So T associates to each real element A, or every real number A, who associates what? An element in R star. But an element in R star is by definition a function from R to R, a linear function from R to R. And this function, what does it make? It takes x into ax. So if you like, if you put a and x together, we get a bilinear form because it's linear in a and linear in x actually. Okay, so we claim that T is actually an isometric isomorphism or a surjective isometry. Okay, and therefore we could identify R with R star. So what do we need to do? Okay, here's the problem. First of all, we need to check that T is well defined. What do I mean by that? I need to check that TA is really an element in R star. How do I know that TA is an element on R star? It should be linear and continuous. Now, continuity is automatic, as you know, because in general, if the source space is finite dimensional, any linear map is automatically continuous, as you may know. Okay? And we can prove continuity. It's not difficult, but it's automatic. So just have to prove that TA is linear in X. And this is, of course, trivial. Okay? So this is what I mean by T is well defined. So it really maps R into R star. Okay, second thing, T is linear, but linear in A, not in X. Okay, so first property, it's linearity in X. Second property is linearity in A. So TA plus B is TA plus TB, and T alpha A is alpha TA. And this is, of course, trivial. Okay, now I will write them. And we have to prove that T is surjective, and the norm, and T conserve the norm. So the norm of TA is the norm of A, but the norm of A is just the absolute value of A because A is a real number. Now, you may, of course, prove that directly that T is injective, but you don't need to do this because if you prove this isometric property, then this necessarily implies that T is injective because if T is a linear operator and TA is 0, then A must be 0. Okay, so, and that's it. So we need to prove that all these 4 properties. So let us write them as you should do that in an exam. Okay, so why TA is an element in R star? Okay, because So I have to check that TA is a linear map. Okay, now as I said, this is straightforward. Okay, because T of x plus y is TA of x times TA of y, and so on. Okay, so just as we said, for simplicity, instead of writing TA of x, we can write TAX. Okay, and now, but so let us write it just once to really understand what you should do in such situations. But everything is trivial. So T of x plus alpha y is by definition A of x plus alpha y, and this is alpha x plus alpha ay, which is just TA of x, TA evaluated at x plus alpha TA evaluated at y. So this is the first point. TA is really a linear map between R and R, and of course it's continuous. Okay, and you can check continuity directly, but you don't need to because, as you said, R is finite dimensional. So, okay, second point. Okay, now we check linearity in A. Okay, so I take a scalar lambda and two vectors A and B in R and an element X in R. Okay, so let us evaluate T of A plus lambda V at the point X. So by definition, this is A plus lambda B times X, and I split it into two parts. And of course, I get TA evaluated at X plus lambda TB evaluated at X, which is the same as, this is equal here, this is equal to TA plus lambda TB evaluated at X by definition of the sum of two functions. But since this is true for every X, we get TA plus lambda B equal TA plus lambda TB. And this proves the second point. So very trivial, actually. But this methodology actually will apply it in a less trivial case. So we have to understand first what happens in such very simple situations. So as we said, points 1 and 2 together mean that this form is linear in X and A. Okay, so this is what we just checked. So it's a bilinear map if I consider it as a function of two values. Okay, third point, surjectivity. How do you know that T is surjective? Okay, take an element in R star, which is the source space of T. Okay, if X is a real number, we can write X as X times 1. But since F is linear and X is a real number now, we can put X outside. So it's just X F of 1. So if you set A to be F of 1, so what do we get? We get F of X equal TA evaluated at X. But this is true for every X. So this means that F equal TA, and this is just surjectivity. Okay, so for every element F in R star, we can find an element A in R whose image under T is F. So this is surjectivity, straightforward. Now, conservation of norms, also straightforward. We go back to the definition. The norm of TA, because TA now is an element in the dual, this is the operator norm. So by definition, is the supremum. I can, of course, drop the absolute value. It's the supremum of TA evaluated at X for X in the unit ball of what? Of R. The unit ball of R is just the segment, the straight line segment, the segment minus 1, 1 closed. Okay? So go back to the definition. This is just absolute A, absolute X. And as you may check, this is just absolute A, because the supremum is a maximum here. So just when X equal 1 or minus 1, we get absolute A. So we really have the conservation of norms. Therefore, T is an isometry, and since it's surjective, it's an isometric isomorphism. And yeah, so this is in a very trivial. So I illustrated the methodology that you need to do on a very trivial example. Okay, and it's important to understand what we did here, because last year in the exam I asked something similar, but of course with LP spaces, and no one did it completely. Okay, so okay, now more generally, let us consider the dual, let us see what is the dual of R to the n when I equip Rn with the Euclidean norm. Of course, I can equip Rn with any norm I like, but if I change the norm, I don't get an isometry actually. You can get, well, I need, yeah. So let us first understand what happens with the Euclidean norm, because if I change the norm, I get an isometry actually, but not necessarily I get an isomorphism, but which is not necessarily an isometry. Okay, anyway, so fix the Euclidean norm on Rn. And I claim now that the dual of Rn is isometric to Rn. Okay, so can identify Rn with its dual. Okay, exactly same methodology. But now instead of taking an element A in R, I take an n tuple, an element in Rn, and do the same construction. So we consider the operator T sending Rn into its dual, and to each element A in Rn, we associate what? A linear bounded map from Rn into R. So Ta is a linear map, which is just the dot product between A and X. So exactly the same thing as we did in one dimension. Okay, so first thing, and this is my isometric isomorphism. Okay, so the conclusion is that I can identify the dual of Rn with Rn. And same procedure, points 1 and 2 should be straightforward. Okay, so Ta is well defined, it's really linear in X. Second point is linear in A. Third point, less trivial, we have to take a basis. So we take the canonical basis. So we take E1 to be 1, 0, 0, 0, 0, E2 equals 0, 1, 0, 0, and so on. This is called the canonical basis of Rn. And now, if F is in R, this is the dual actually. So there's an error here. It's Rn star, not Rn. Okay, because we don't know yet that they are the same thing. So F, so usually we write the element of a vector by X and the element of its dual by F or G and so on. We shall go back to this later. So now, if X is in Rn, and so we can decompose X in this basis. So X can be written as sum of Xi EI, so Xi are the components of X, if you like. And if F is the linear map is in the dual of Rn, then F of X is actually F of the sum. But since F is linear, F of the linear combination is the linear combination of the images. So this is just sum of Xi F of EI. And so if I let small I to be F of AI, then F of X would just be this dot product between A and X, which is just the A of X. So since X was arbitrary, this means that F equal TA. So this is just the surjectivity of T. So T is surjective. Okay, so same thing, same methodology. And fourth point, first point is a consequence of the Cauchy-Schwarz inequality. So in absolute value, this dot product is less than the norm of A, the Euclidean norm, times the Euclidean norm of X. Okay, this is the Cauchy-Schwarz inequality. And therefore, what this means is that in absolute value, TA of X is less than norm A times norm X. So the supremum over the unit ball is just this, and this is less than the supremum of norm A, norm X, which is just norm A. So we get already one half of the equality. So norm of TA is less or equal than A. Okay. Now, converse is less trivial. We have to prove that norm of TA is bigger or equal than norm of A. So we may assume that A is different from 0, because if A equals 0, of course T0 equals 0, so they have the same norm. It's not interesting. And now we take X to be A over its norm. So it's a unit vector. It's a vector on the unit sphere. Okay, now the norm of TA is bigger or equal than TA evaluated at X for X because, by definition, because this is the supremum. Okay, so this x is in the unit sphere. Yeah, we can put here norm of x equal to 1, actually, as we said. So we can take the supremum over the unit closed unit ball or the unit sphere, same thing. So by definition of the norm of TA, because this is the maximum or the supremum of this. Of course, in finite dimensional spaces, because the closed unit ball is compact, then the supremum is a maximum. Okay, it's not a big deal. So this is the maximum of this. So it's bigger than TAX. But what is TAX? I go back to the definition. So this is TA evaluated at A over its norm. And by linearity, I can put the constant outside. So it's just 1 over norm of A times TA evaluated at A by linearity. And we go back to the definition. So TA evaluated at A is just the norm square of A, right, by definition. So it's norm square of A divided by norm of A, and this is just norm of A. So we have a double inequality and therefore equality. So this finishes the proof that T is an isometric isomorphism between Rn and its dual. Okay. So we can identify Rn with its dual if we put the Euclidean norm. Okay. Now in the exercises of chapter 2, we explore what happens if we put another norm on Rn, not the Euclidean norm. For example, the norm 1 or the norm infinity, or more generally the norm P. What happens in this case? The result is still the same, but we have to put another norm on the dual. Okay. Okay. More generally, if you have a Hilbert space, the dual of a Hilbert space is isometric to itself, to the Hilbert space. Okay. Exactly the same procedure, but here we have to use the Reed's representation theorem. So this is just an extension of this example. So same thing. Instead of Rn, we can take a Hilbert space. It's the dual, and so TA is the operator from the Hilbert space into R that to each x associates the dot product between, or the inner product between A and X. So it's a useful exercise to test your understanding. So just rewrite the proof in this more general context of a Hilbert space. Okay, because if you look carefully, all we used here is just the properties of a dot product. But you have to use actually the Reed's representation theorem to prove surjectivity. So here you have to change the third point a little bit. So in the case of Rn, we use the fact that we have a finite basis. But if you have an arbitrary Hilbert space, this argument does not work actually. So you need to invoke the Reed's representation theorem that tells you that every element in the dual of a Hilbert space is a dot product. Okay, so but it's the same strategy. Okay, now let's review. What is the dual of L1? L1, as you may know, is the space of infinite sequences, which are the series of their general term is absolutely convergent. Okay, so this is a classical example of a Banach space under the norm 1, which is the sum of the series of absolute values. Okay, so what is the dual of L1? Okay, or what does it look like? Actually, we'll prove that it's isometrically isomorphic to L infinity. What is L infinity? L infinity, as you may know from second year, is the space of all bounded infinite sequences with the norm supremum, with the subnorm. Okay. Now, so it's exactly the same procedure. We consider the operator T from L infinity to the dual of L1, that to each A associates a bounded linear map, that to each X associates this dot product. Okay, so here we have to, so we follow the same methodology. Linearity in X, so we need to check linearity in X because TA should really belong to L1 star, and of course because this is a dot product. And but here continuity is less trivial because L1 is infinite dimensional. So why this is continuous in X? Because TA evaluated at X, the absolute value of the sum is less than the sum of the absolute values. And now, if A is in L infinity, then so A is a sequence, A1, A2, etc. So A and each term of the sequence is less than the norm of the sequence because it's the supremum. So now this does not depend on N, so I can put it outside and I get norm infinity times this series, which is just norm infinity times norm of X. So this means this is continuity in X. So TA is really a linear bounded map from L1 to R. So it's an element of the dual. Okay. And linearity in A, same thing, not terribly difficult because so actually T, if you consider T as a function of A and X, it's bilinear, linear in A and linear in X. So this should be clear. Third point is a little bit delicate because we are dealing here with infinite series. So we must address the issue of convergence. Okay. Now consider the following vectors or the following element in L1 and as well as in L infinity. So this is the analog of the canonical basis, if you like, of Rn. So E1 is just the sequence whose first term is 1, the remaining 0, E2, second term 1, remaining 0, and so on. So you have just to pay attention that this is not an algebraic basis of L1, but it is what we call a Schauder basis of L1 in a sense that I will describe now. Okay, so if you take now an arbitrary point in L1, which is just an infinite sequence, the series of the general term xnen, it's now actually, this is a series in L1 because En is a vector and xn is a scalar. So this is a series in the norm space L1, okay? And I claim that it converges, okay, to what? To X in the norm L1. How do I know that? I go back to the definition of convergence. How do I know that a series is convergent in a norm space? Okay, this happens when the sequence of partial sums converges. Okay, so we consider the sequence of partial sums. So instead of going to infinity, we go up to a certain integer n. So this is the sequence of partial sums. So we evaluate the distance between x and this partial sum. Now in norm L1. So x is now a sequence, infinite sequence as we know. This partial sum actually, as when you evaluate it, actually is just an infinite sequence whose first n terms are x1, x2, xn, right? Just go back to the definition, and all the remaining are 0. Okay? So it's just the distance between two vectors and norm spaces. And we have to evaluate the norm 1 of this difference. So when you do the difference, okay, the first n component will cancel with each other. So we just get the norm 1 of this sequence whose first n components are 0. And what's that? What is the norm L1 of this sequence? It's just the sum of absolute values. So it's absolute 0 plus absolute 0 plus absolute 0 plus absolute this plus absolute this. So just the remainder of the series. So it's this the series starting from n plus 1 of the absolute value of xk. Okay? And now this is the remainder of a convergent series because x is in L1. Right? So we know that as n tends to infinity, this term, this real number tends to 0. So this precisely means that this sequence converges to x, okay? Which just means that this series converges to x, okay? So this is the meaning when we say that E1, E2, etc. is a Schauder basis, okay? So not at all, not trivial, so we have to do some work here. Okay, so we can write X as this infinite series. Okay, so here you have to understand that X is a vector in an infinite dimensional space. En are vectors, but small xn are real numbers. So this is, if you like, it's an infinite linear combination of elements of E of the set. But once again, here we proved convergence. Okay, so it's not an algebraic combination, because an algebraic combination is finite, but here this series is infinite. Okay, so now having this point, we can prove now surjectivity. Okay, so if we take an element in the dual of L1, we don't know what this is yet, so it's linear and continuous. Therefore, f of x is f of this series. But now continuity permits me to exchange summation and f. Because what's that? It's f of the limit of a sequence. But continuity tells me that f of the limit is limit of f. So it's the series of f of x and en. And by linearity, I can put xn outside because it's a real number. So this is just the series whose general term is xn f of en. And now this is a series of real numbers. Now here everything is real. Xn is real and f of en is real, but f is in the dual space. Okay, so if I put for each n, an equal f of en, I get, no, the norm, observe that the norm of en, the norm 1 of en is 1, because this is the 1 plus 0 plus 0. And since f is bounded, the sequence an is bounded, right? Because f is bounded on the unit sphere. So this is less than a certain constant. And therefore, if you denote by A the sequence of elements an, so A is the infinite list A1, A2, An, etc., then since this is a bounded sequence, then A is an L infinity. And we can write now, it's just straightforward. So f of x is now sigma of xn an, which is just an xn. So it's just the A of x. But this is true for every x. Okay, there was no restriction on x. And therefore, this means that f equal ta. So this proves surjectivity. We started with an arbitrary element in the dual of L1, and we found an element in L infinity whose image under T is f. So this is surjectivity. Now, conservation of norms, we already did half of the work. The identity, the inequality that we established here in part 1 to prove that Ta is well defined tells me that Ta of x is less than this product. So when I take the supremum over the unit ball, I get norm of Ta is less than norm of A. Infinity, of course. Yeah, because I think I put infinity here. Yeah, exactly. Okay, now for the reverse inequality, we use a familiar trick to prove that Ta is bigger than A infinity, a norm. It's just enough to prove that norm of Ta is bigger than norm of A infinity minus epsilon for every epsilon. Okay, so we pick an arbitrary positive number, epsilon. Now, what is the norm infinity of A? The norm infinity is the supremum of An. But by a property of the supremum, as you know, norm A infinity minus epsilon, since it's strictly less than the supremum, is not an upper bound. So we can find an element of the sequence AK, which is strictly bigger than the supremum minus epsilon. Okay, this is a well-known property that we use several times. Okay, just one index K is enough. Now, as you observe, the norm 1 of Ek of this sequence of vectors is 1. And if you evaluate Ta at Ek, this is just the dot product. So sigma of An Ekn. So if you go back to the definition, all terms of the series vanish except one, which is just Ak times 1. So it's easy to see that Ta of Ek is just Ak. And Ek is in the unit sphere. So therefore, by definition of the norm of TA is bigger or equal than the absolute value of TA evaluated at 2. We used this before actually because EK is on the unit sphere, and this is the supremum of TA of x in the unit sphere. So, and this is just norm of EK, AK, absolute value of AK, which is by construction bigger or equal than norm A infinity minus epsilon. And since epsilon was arbitrary, I let epsilon tend to 0, and I get norm of TA bigger or equal than norm A infinity, and therefore we have equality, and therefore T is an isometric isomorphism. Okay. So once again, this, don't confuse, this is the operator norm. So this is the norm in the dual of L1, and this is the norm in L infinity. Okay. So this example permits me to identify the dual of L1 with L infinity. Okay. So it's a really fundamental example. Okay, now same idea, but more general. If I pick a number P, which is at least 1, and I consider the space small lp that you probably encountered in second year, the space of infinite functions as well, that such that this series is convergent. And on the space, we put this norm, the LP norm, that you should be familiar with. And we claim now that the dual of this space of sequences is also isometrically isomorphic to another LP space, which is LP prime, where P prime is the conjugate of P. Okay, the conjugate of a real number bigger or equal than 1 is the number actually P over P minus 1, or equivalently P plus P prime equal P prime, with the convention actually that if P equal 1, so the previous result was an extreme case of this. When P equal 1, then P prime is plus infinity, because 1 over infinity is 0. Okay, so in order to avoid this extreme case, we could write here strictly bigger than 1. Okay, but we can put also bigger or equal than 1, because when P equal 1, we get the previous case. So here actually, but I will not prove that, because you can do it actually if you follow the same methodology that we did so far. So 4 points, you can do that, and actually it's the same formula. Okay, dot product. So do it as an exercise if you like, but if you don't do it, it's okay, because we shall prove a much more general theorem in chapter 5 about LP spaces. So this is a particular case of what we call LP spaces. Okay, and yeah, I did that. I gave that the last example. Actually, I gave it last year as an examination question. So we consider the space of all sequences that converges to 0, and it's denoted by small c sub 0. Okay, and we equip it with the infinity norm. So c sub 0 actually is a subspace of L infinity, because a convergent sequence to 0, a convergent sequence is bounded. Okay, and now the dual of C0 is isometrically isomorphic to L1, and it's exactly the same thing. Okay, just copy paste, but pay attention to the notion of convergence. So you have to use the Schauder basis, the canonical Schauder basis, E1, E2, etc. So it's easily done. So I suggest that you do it as an exercise. Sorry. Yeah. And yeah, last example, the space of continuous functions on 0, 1, denoted in this way. You can drop the parentheses actually. This is the modern notation used by functional analysts. To simplify, we drop the parentheses. And this is the norm of uniform convergence, or the supremum norm. And it's the maximum actually. The sup is a maximum here, because if U is continuous, then and 0, 1 is compact, then the supremum is a maximum. Now, it's a little bit difficult to describe the dual of C0, 1, but I just want to give you an idea. It's actually isometric to a space of measures. Okay, but we need to introduce the notion, we need to extend the notion of measure, because we learned the notion of positive measures. There's also the notion of signed measures. A signed measure can take negative values as well, but the series must be convergent. Okay, so in order, and you can put a norm on the space of measures. Okay, now the key to this description, so the dual of C01 is isometric to a space of measures with some norm, is a very important theorem, representation theorem due to Reitz, that you should know. Okay, so a Borel measure on a topological space is a signed measure. Signed measure, as I said, is just an extension of the notion of measure. It does not take the value plus infinity, okay, but it can take negative values. So a Borel measure on a topological space is a signed measure defined on the Borel sigma algebra of that space. Okay? And here is the Reitz representation theorem that you should know, at least. If F is in the dual of C01, so it's a linear bounded map from C01 to R, then we can represent F as an integral. So there exists a Borel measure, a signed measure, on 01, such that F of u, this is a real number, is the integral over 01 of u, the continuous function, with respect to the measure mu. Okay, and this we have to take actually a signed measure, because this is something that could be negative, right? So this is known as the Reitz representation theorem for the dual of C01. Okay, so here actually where the isometry associates to each f the measure mu. Okay. Now I'm not going to prove that; it's a little bit difficult. But this is the isometry. So we identify f with the measure. Okay. And I think this is the last example. Okay. Now the main result in the main remaining result that we shall prove is the non-compactness of the closed unit ball in an infinite dimension space. Okay, and this is what makes the study of infinite dimensional spaces more difficult than the finite dimensional ones. Okay, first thing is that continuity is not automatic in infinite dimensional spaces. So there's all. Okay, so recall first that a finite dimensional space is isomorphic with Rn, where n is the dimension of E, and I think you proved that in second year. It's not this terribly difficult. Just take a basis and so therefore a finite dimensional North space is a Banach space. It's always complete, and actually all the norms are equivalent in the finite dimensional North space. Okay, so therefore if a finite dimensional subspace of a norm space is closed in that space always. So finite dimensional spaces are closed. So now, yeah, so this is, I think, the last result. It's due to Reitz. The closed unit ball of a normal space is compact if and only if E is finite dimensional. This is the main result that we shall prove. So if E is infinite dimensional, the closed unit ball and this unit sphere as well are non-compact. And this is one of the difficulties, as I said. So there are two implications here. But to prove this is the final and main result. We need a lemma. It's known as the least distance to a finite dimensional. So if we have a normal space E and a finite dimensional subspace of E called F, and we take an element x in E, then the distance between x and F is actually achieved at some point x0. So the infimum is the minimum here in this case. This is not always true, as you know. We have counterexamples. But what is this lemma saying is that the infimum is a minimum. How do I know that? Okay, there are two proofs. I will just give you one of them. The other is in the lecture notes. But I find this a little bit easier than the other one to understand. So we go back to a property of the infimum. Since this is an infimum, it means that there exists a sequence an in F that converges to the infimum. Okay, same thing for the supremum. So by a property of the infimum, we can find a sequence an in this finite dimensional space whose distance to x converges to this distance. So in particular, this sequence is bounded from above because it's convergent. Okay. So therefore, an is bounded as well by the triangle inequality. Okay. So if we set R to be m plus the norm of x, then this sequence an belongs to F and to the closed ball of center 0 and radius r. Okay, in the space E. Now, this set is closed and bounded and lives in a finite dimensional space. So we know that in a finite dimensional space, closed and bounded sets are compact. Okay, this is something that we proved in the topology course and also in probably know from second semester of second year. So if it's compact, then it's sequentially compact. So this means that an has a convergent subsequence, ank, that converges in that space. So it belongs to F. So the limit belongs to F. And now we are done. If a and k converge to x0, then by continuity of the norm of x minus a and k converge to the norm of x minus x0. But norm of x minus a and k as a subsequence of this converges to dxf. Therefore, by uniqueness of limits, we have equality. So therefore, we have the infimum as a minimum. Okay. Now I use this to prove the famous least representation theorem. Now there is an easy part, which you know from second year. When E is finite dimensional, actually I used this result in the proof of but this is straight. I should have said this before, but okay. Why in a finite dimensional space a closed bounded set is compact? Because as you know, if E is finite dimension space and has dimension n, then there is an isomorphism between E and Rn. Okay, and now B is closed, and since L is a homeomorphism, L of B is closed, and since L is continuous, so it maps bounded set to bounded set, so L of B is bounded, so L of BE is closed and bounded, therefore it's compact, and therefore its inverse image. Its image under L minus 1 is compact. Okay, but yeah, so the inverse image of the image is just so this is, I think you encountered this argument in second year because in topology you proved that every closed and bounded subset of Rn is compact. But so this relation extends to any finite dimension space. And by the way, so as you know, I used this result in the proof of but there's no circularity here. Okay. Now, the interesting part, what if E is infinite dimensional? Okay, we shall prove that B is not compact if E is infinite dimensional. So first, pick an element of E whose norm is 1, and this is possible because E is not trivial if it's infinite dimension. So I can always find an element in the unit sphere. And now consider the space E1 spanned by E1. So this is just the line through E1. Now, since the dimension of E is infinite, then E1 cannot be equal to E. Okay? So we can find an element in E which is not in E1. I call it X. Okay? By the lemma, since E1 is finite dimensional, the distance between X and the space E1 is achieved at some point Y in E1. But since X is not in E1 and Y is in E1, so X is different from Y, and therefore this is something positive. So therefore I can divide by the norm of X minus Y. And now I let E2 to be X minus Y divided by its norm. So it's again an element in the unit sphere. Okay? And if I evaluate the distance between E2 and E1 from the first step, just replace E2 by its value. And reduce to the same denominator if you like, and put this real number outside the norm. So you get x minus y minus e1 times this norm, right? So I can put, I can rearrange that. So x is here minus y minus this multiple of e1. Why did I do this in this way? Because now, okay, norm of x minus y times e1 is in e1, right? And y is in e1. So this term is in e1. Therefore, this is norm of x, the distance between x and the element of e1. So it's bigger than the infimum. So this guy is bigger than dx e1, this guy here. Okay, so I get 1 over norm of x minus y times this distance is just x minus y. So this is just bigger or equal than norm of x minus y over x minus y, and this is 1. Okay, so just go back to the definition. Okay, so now E2 is at least at a distance 1 from E1. Okay, and I continue. Now I consider E2 to be the space generated by E1 and E2. Now, as you may check, you can check actually that E2 is linearly independent from E1. It's not difficult. But since the space is infinite dimensional, then E2 cannot be equal to E. Okay, so I can find an element in E2 that I will denote by x, but it's not the same x as in the previous step. So I can find x in E, not in E2. And I use the lemma to get another y, not the same as before, where the distance is achieved. So I can find y in E2, where no distance between x and y is the distance between x and E2, and this is something positive. And once again, I put E3 to be this norm vector, so this is E3, so it's in the unit sphere. And if I try to evaluate E3 minus E1, I do the same thing. Now y is in E2, and E1 is in E2 as well, because now I have an increasing sequence. So as you noticed, E2 contains E1. So this guy here is in E2, and as before, this is bigger than the infimum, which is a norm of x minus norm of y, so this is at least 1. And same thing, if I evaluate the distance between E3 and E2, I get the same thing. So, and I can continue, okay? And then I take the span of E1, E2, E3, and I continue this. So if continuing to infinity, we have an infinite sequence En in the unit sphere, actually, such that the distance between any two distinct terms is at least 1. Okay, and that's it. So this inequality prevents En to having a convergent subsequence. Okay, so we have now a sequence in SE with no convergent subsequence. Okay, because here, if you take ENK, ENL, even if they are big enough, if k is different from L, the distance is 1, so it cannot be less than epsilon. Okay, so it's not a Cauchy sequence, if you like. Cannot contain any Cauchy subsequence. Okay. Therefore, this proves the non-compactness of the unit sphere and also the non-compactness of the unit ball. Same thing. Okay. And now, as an exercise, as I told you in the proof, that the whole set obtained in the construction is actually linearly independent. Try to prove that. Okay, and so as we said also, the unit sphere in an infinite dimensional space is also not compact. And this lack of compactness in the infinite dimensional case is the main motivation behind the introduction of topologies that are smaller or weaker than the norm topology. Okay, so as I said in the previous video, a weaker topology has more compact sets and more convergent sequences, and these two notions are very important in analysis. Okay, now there is another proof, shorter actually, a little bit shorter, but I like this proof because it tells you the reason why. Where did we use the infinite? If what does it in the previous proof breaks down if E is finite dimension, because you cannot continue forever. If the dimension of E is n, then at some point E will be equal to En. So we stop. Okay. So this is where, so when we have infinitely many dimensions, we can construct an infinite set which is linear independent, and the distance between any two distinct points is at least 1. Okay, so cannot contain any convergent sequence. Okay, and so this concludes the main result. But now I will just end with some words about topological complements and quotient spaces. We encountered the notion of algebraic complements in the previous video. Now, the topological complement of a closed space, closed subspace of a null space E, is a closed subspace, another closed subspace, such that E is the direct algebraic sum of f and g. Okay, so the difference between algebraic quotient, topological complement, and algebraic complement is that we require now that the two spaces are closed, to be closed. Okay. Now, we know that, to observe that an algebraic so every subspace has an algebraic complement, but it's not true that every closed subspace of a normal subspace space has a topological complement. Okay, there are many counterexamples, but in some cases, yes. So first result that you may prove after studying chapter 3 is that a closed subspace of a Banach space has a topological complement if and only if the projection onto F is continuous. Okay, this is the first result. That second result that you may encounter in second year: every closed subspace of a Hilbert space has a topological complement, because actually this is essentially because of the Riesz representation theorem and orthogonal projections. Okay, in an arbitrary normal space you don't have the notion of orthogonality because you don't have the notion of a scalar product. Okay, and after studying chapter 2, you will be able to prove that every finite dimensional subspace of a normal space has a topological complement. And the fourth result is easy, actually, you can prove it now. Every closed subspace with finite codimension has a topological complement. Okay. And yeah, now I will talk about quotient spaces. So we define the quotient space of a vector space over by a subspace of it. So this is a vector space, but now we can put a norm on this quotient space by letting the norm. So an element of this quotient space is just a class, an equivalence class, denoted by this symbol. So I put norm of the class containing x is just the distance between x and f. And then you can easily check that this is defined in norm. And if E is a Banach space, then the quotient space is also a Banach space for this norm. It's not difficult, you can do it. And last result in this lengthy video, the completion of a norm space is important. I will not prove this theorem, but you have to know it. If we have an arbitrary norm space, then there exists another Banach space, E tilde, equipped with a norm prime. Okay, so first thing, it's a Banach space. Second thing, this new norm extends, is an extension of the old norm on E. And third property is that E is dense in this new space. And in some sense, this is called the completion of E. And if F is another space satisfying these three properties, then F is isometric to E star. Okay, so otherwise stated, if I have an incomplete normal space, then I can embed it in a bigger one which is complete. Okay. Now, when we study in chapter 2, when we study the bidual, we can prove this actually. But I'm not going to prove this last, the uniqueness, if you like, okay? Because in chapter 2, we will embed E in its bidual, and the bidual is always complete, okay? Yeah. And here's an example. If you take the space of all Riemann integrable functions on a closed interval EB, and you equip it not with the subnorm, but with the one norm, okay, then you may prove that the completion of E is isomorphic to the space L1 of all Lebesgue summable functions on 0, 1. Now, 0, 1 closed or open doesn't change anything because the measure of 0 is of a singleton is 0. So actually, L1 of 0, 1 closed or open is the same thing. Okay. Now try to think of this. Why is it true? We know that L1 is a Banach space, but this is not a Banach space. Okay. So this is why LP spaces are important, because they are Banach space. Okay. And this is why the Lebesgue theory is stronger than the Riemann theory, because the Riemann, if I just restrict myself to Riemann integrable functions, I don't get complete spaces. And many results in functional analysis are not true if we remove the completeness assumption. So we need to work in Banach spaces. Okay. So this concludes this lengthy video on norm spaces and Banach spaces, and this concludes also chapter 0 as well. In the next video, I'm going to solve some selected exercises. It's not necessary to solve them all, but I will just solve the exercises whose results will be needed later. Okay, because so as you observe, a big part of this preliminary chapter was a review, so there was nothing new. Okay, so thank you for your attention and see you next time.